Record. Good evening, everybody. Those of you that are joining us in real time tonight, and those of you who will be joining offline through our YouTube channel at some point in the future. You're all very welcome. This meeting is one of the results from the very first meeting we had, and you'll see from our webpage there's a full program of Friday evenings right up till July. I have to say thank you so much for the enthusiasm and encouragement that I've received personally, and it's been a dream to put the program together because there's just been a fantastic response. John Cook, the director of the radio astronomy section, just at the moment doesn't have audio and video on his computer, and I think he's a bit problematic with bandwidth as well. So John's not with us, but he did send me a message for us, and I'd just like to read that. First, he says, "I must apologize for not taking part in this meeting. I don't have suitable equipment or fast enough internet connection. My plans on taking over as section director were to organize general meetings during 2020. Events rather overtook things, so that came to nothing. When conditions allow, I will see what I can arrange. I'd also agreed to take part in a couple of other BAA meetings and events in 2020, all cancelled or postponed. Our past meetings have proved to be very popular and well attended, so I look forward to the next opportunity to meet and display our work. Meanwhile, I continue to circulate the monthly activity summary on all areas of radio astronomy that are reported. VLF solar flare monitoring has always been at the center of this, but it has expanded over the years to include magnetic, meteor and atmospherics. An archive of the summary is available through the section pages of the BAA website. I have to thank John Berman for all his work on the website with regular updates each month. My annual review of the section work has been sent for publication and should be either in the April or June issue of the journal. The Starbase team have been working on Schumann resonance receiver, so I look forward to seeing some results from that. It's been a tricky system to design given the very low signal levels involved and at very low frequencies and rather aerial required. I'd also be pleased to hear work of other areas of radio astronomy being investigated. My thanks to Paul for arranging this event. John Cook, section director. So that was the message from John for this evening. I had a message just this afternoon from Derek Robson, and he is meteor hunting this weekend with the EAARO. So I'm meteorite hunting. So he's on a hunt for bits. I don't know how successful that would be. It sounds like it's extremely difficult. Anyway, I've asked him to share with us if he's got anything interesting next time he's with us. You will have seen two training events organised. I hope that there'll be more in the future. Do check out the dates and times on the BAA website on our section. RAG 21 day conference is coming together. By the time we meet in a fortnight's time, then we shall have some more hard information about that. And our next meeting, RAG Zoom 3, SIDS and TIDS, the ups and downs of the ionosphere. Mark Edwards. Thank you, Mark. Anyway, tonight, enough of me chatting on. Tonight we've got John Berman is going to present Radio Meteor Detection Collaboration Project. So John, it's all yours. Let me know if you can't share your screen. I think I set it up to do that. Is John with us?
Yes, I can see him.
Yes, you'd think I'd know how to unmute after spending a year at home, wouldn't you? But apparently I don't. So there you go. Right, let's see if I can share my screen. No, it's just you've disabled it. Can you enable, please?
Oh dear. Oh, it's in security, isn't it?
Yeah, somewhere.
Oh yeah, sorry, it was. It
Was
was not allowed. I'm sorry. Apologies. Should have it now.
Let's have a go. So what do I do now? It says share screen. I've clicked on it. Oh,
And
there we go. Oh, can I? Oh, I just
we've
want
got
to
more.
share my. So I just want to share my whole screen. There we are. So because then I can just select what I want. So ignore that text
Oh,
file.
it's working.
Hey, right. Let's get this up. So if I speak too quickly, someone shout and let me know, please. If I'm not articulate enough or you can't hear me, again, please do let me know. And I've sort of, yeah, but we'll see how it goes. Look, I suppose we'll save questions for the end, and someone hopefully will field those for me. So anyway, thank you very much for letting me present this evening. It's appreciated. And this is all about the Radio Meteor Detection Collaboration Project. So whilst it's about the detection of meteors by radio, it's not about how we detect meteors by radio. That'll be no doubt the subject of somebody else's talk at some point. This is more about what are we doing with the data that we collect. So hopefully that's clear and obvious. So I've got quite a number of slides and I won't go too fast. So the first one really is, what is our project about? So when I started getting interested in radio meteors back in about 2016, got fed up with cloud and being in every night, not being able to do anything. This interested me, and I started off with a fairly simple setup, which I still have and works, using instructions provided by Paul Hyde. Thank you very much. And it didn't take me long to realise that occasionally you get quite a long event. You think, oh, that's interesting. And the first question that sprung to mind really was, who else got that long event? So there were lots of chit chat on forums. Oh, yeah, we got that one. We got that one. And because I'm a bit of a techie in the background and I like messing around with data, I thought this lends itself to a database. Perhaps we can get everyone's data in there, and then we won't have to ask that question. We can just go and have a look. You can search by a date and a time and see what you can find. So that's how it was born. It has, however, moved on somewhat. So we started in Jan 2017. We have 5.7 million individual events now recorded, which is quite a lot of data. And we have some 16 regular contributors. And you can see on the, I'm assuming you can see this quite well. You can see on the screen, we're quite spread out. We have someone quite far up north now, which is good. So we have a lot of data. We have a lot of contributors, which is excellent. So after the initial idea of, well, does anyone else see that event? We sort of thought about, well, we've got a database with all the events in. Can we sort of mess around and do some queries and stuff and see if we can find any matches? It's a lot harder than you think, because there's almost two, but there's a couple of factors. One is obviously everyone's station is slightly different. Everyone's timings are slightly different, although most of us do use an internet-based timing service, but everyone's time's a little bit different. Everyone's setup's a bit different. Some people's devices that they're using at home to detect are slower than others. Some are faster than others. Some actually, with using Spectrum Lab and a script, will actually record the duration in cycles rather than seconds. So there's a whole number of factors involved, but we can do an element of normalization, which we do with our data. We can try and standardize it as much as we can within reason. And doing all that, there's still a lot of events. So we decided actually the way to do this is probably look at longer events, of which naturally there are less. So we originally started off looking at events that were 10 seconds or longer, which is quite long really for a radio event, but we do get them. And then we look for a match on a date and a time, the time being plus or minus 2 seconds. And how well do we do with that? Reasonably well. So I don't know if you can see these. I can see them quite well, and I will share the presentation afterwards if you can't see them well. But this is just an example of a match that the database has said this is a potential match. So we call them potential until they're confirmed. because they're all potentials, I suppose. But here you can see here, people's durations, look, 12.29, 11.09, 10.58, they're fairly similar. And you can, although the screenshots are probably quite small on the screen, you can actually see that the captures are also remarkably similar. So it's probably fair to say, with a reasonable amount of certainty, that this is the same event. And that was one of our aims. And so for that, we've been successful. We do call them coincidences because until we've really looked at them and said, yeah, that one is a match, it is a coincidence, because it's not an exact science. And I think I'll put another one on here as an idea. So again, this is quite a long event. In fact, very long event, look, ranging from 47 seconds up to 58 seconds. But if you look at the screenshots, they are remarkably similar. If you look at the timings, 12, 21, 22, there is a difference of 3 seconds, which is actually quite a lot in our terms. But again, there's a reasonable expectation that again, this is the same event. And we now do produce, well, I don't, the database is now the way it's coded, it produces when we've imported our monthly data, it produces a list of monthly coincidences. So that's quite successful. So in addition to our original, oh, did you get that? We've now got an additional item here that our database produces every month. Excuse me, a quick sip of my refreshment. That's better. So what else do we do with it, with the data currently? So we produce a monthly trend chart. So we take everyone's data, do a little bit of messing around in Excel, and the black line is the trend for the month. And not surprisingly, given that that's August, you can see the peak for the Perseids, for instance. And we produce the trend every month. And for the major and actually for the minor showers, you do tend to see that the black trend line does seem to highlight when these events take place. Is it useful? Well, I find it interesting, so to me it is. And probably if we did this over time and took showers perhaps over a number of years, it would potentially be even more useful. Probably going quite quickly. I have no idea how I'm doing time-wise because I can't see a clock. I'm guessing I'm doing okay. What else do we do with it? So I did this with it, and I found this quite interesting. So I will talk you through it because initially you think, what on earth is that? So we look at the duration events for a month, and then the database will categorize them. So those that are less than 1 second, these radio events, less than 1 second, 1 to 5, 5 to 10, and greater than 10. And actually, if you look down the columns across the months, and I've sort of started doing this in January 2019, categorize, or the breakdown, or the percentage of events that falls into each category is fairly similar across every month. The only times it tends to differ is when we have a major shower. So if you look at August, for instance, if you look, can I point with my mouse? I don't know if you can see my mouse, but if you go down the 1 second column, I mean, June was 89, but if you go to August, 84. So in August, out of the total number of events, 84% were 1 second or less. But at the other end of the scale, greater than 10 seconds, 1.3%. So again, probably should be expected with major meteor showers, you're probably going to get larger radio events. But I find it interesting, and that is something that we tend to do every month. And they do tend to stay fairly similar every month. So that's what we do with our Meteor data to date. I'm sure there's more, and I've got questions at the end to ask. So with a reasonable amount of certainty, we can now each month produce a report that shows coincidences. And on the database, you can go in there, it's available to anybody, you can look at those events, you can export them to Excel if you want to study them, along with the captions as well. So it's potentially quite useful. So moving forward, now we can do potential radio matches. We're starting to look at video and radio matches, which is something else altogether. It was tough enough to actually get radio matches. Now we're trying to add video. So given the sheer volume actually of radio and video events, We started off by looking at ways of narrowing the search. Where are we going to look? Oops. Oh. So to start with, to define our area of interest, as we'll call it, and you'll see it later, we started thinking, well, we're all detecting meteors, but actually, for the majority of us, we often capture the ISS going past. It's quite a regular event for us, and through the month, it passes through our area on a pretty regular basis. So some of our contributors are very diligently been capturing the ISS over a period of a month. And we take the date and the time of their capture. We use an API lookup that tells us where the ISS actually was at that date and time and its altitude. And then it's possible, as you can see on the screen, and I had a lot of help from Mike German on this, we can interpolate the position where the line passes through the start of the Meteor ablation altitudes at 120 kilometers. So if I move on a slide. So this is just Mike's contribution. Later on, you'll see the whole thing put together. But this shows where Mike actually detected, no, he didn't. Sorry, this is the map where Mike actually detected the ISS. The circles represent where the ISS actually was at the time that he detected it. And it's probably where we expected it to be fair, to the south of us. It doesn't come too far north. But this shows where he detected it. And then we take that data and we use the API and a bit of an Excel macro that Mike created. And we take these positions and then we adjust them for the Meteor layer. As you can see, if I flick between, they actually all move down a little bit. So these are places where Mike might detect radio events. You can't definitely say he will, but it gives us an area to think about looking when we're considering radio and video. So this area is where Mike will potentially find, detect radio events. And we've done a similar map for all our other contributors. So we take the radio data map, which I talked about. We've added the 1200 kilometer theoretical radio horizons as circles, and then we've shaded an area of our map. And I put a little note at the bottom there. So we're quite confident of how far to the south to look, but given the ISS only goes so far north, we've made an assumption and extended our area of interest up to the south coast of the UK. And when we put all that data together, that's what we end up with. So that the different colors in the shaded sort of rectangle are the different contributors. The circles, I've zoomed in quite a bit here. The circles you can see again are our contributors' theoretical radio horizons. And so taking those horizons into account, taking into account where they actually detect, potentially might detect radio events, we've created this sort of rectangle shaded area. So that's the area where we're particularly interested in looking at finding video events and then seeing if we can find radio events that potentially might match them. Excuse me, just a second. It's tea, by the way, it's not beer, just like they do on the telly. So that's what we do for our, so that's our group radio map, and all these maps are available on online on our website. So they're free for anyone to have a look and have a play around with. So what do we do next? We then start to add some video detections on there. So you'll see towards the top I've highlighted them with blue arrows. So these are video tracks that we've added, and we took these. I took these two semi-randomly because they fall within our area of interest, and we're thinking, well, if the video event is in our area of interest, then there is the potential that we've actually caught a matching radio event. And if I go to the next one, here's an example of where a possible match for a video event. And actually, if I flick back to the screen, oops, sorry, it's the lower one of the two. And you'll see the video event at the top and its source. And actually, I apologize. The top row where it says possible match is should have a header row, but when I took the picture, I cut it off. But it does give its start latitude and longitude, its end latitude and longitude, and its height at the start and the end. And that's done by taking the source data and putting it into a program called UFO Orbit, which I'm sure many of you are aware of. Then it gives you the start and the end and the heights. And it also gives you the time, which is obviously quite crucial. And the block of data beneath, although it's quite small on your screen potentially, so this is a potential match for that video event. The time is so the video event was 05:10:07, and our times range from 05:10:08 to 0:10. If you look at the duration in seconds of our radio events, apart from one, they're all fairly similar. So they are potentially the same radio event. If you could see the pictures, which they're a bit small, they actually look very similar. Not an exact science, but there's a reasonable, it's probably reasonable to say that this is potentially radio matches for the video event. And it's something we only just started doing fairly recently, so we're quite new to it. And I need to tune the query a little bit because obviously time, it's all about time, getting the time accurately. And I think I might have gone so quickly, I'm nearly at the end, but there are a few questions on the screen there. So I'm not going to read them out. I will read them out because they're important. How can we prove our data quality? And I put here, bearing in mind we're amateurs and it is a hobby. You know, so we've got to understand that people do this for, as I say, as a hobby. So we can't be too prescriptive because you put people off. Perhaps thoughts of what more analysis we can undertake with our current radio data that we actually have, and we have a lot of it. And actually thinking about that, what extra data could we start to collect to make it more useful? Thoughts on what we might gain from our video and radio matches. I hope we can gain something from it. Thoughts on where we might take this project moving forward, and any thoughts on possible further collaboration. And that's it, I've finished. I probably whizzed through that at speed, didn't I? Oh no, it's nearly 5 to 8, that's not too bad. I suppose any questions or thoughts, feedback, be appreciated. Thank you.
Yeah, thanks very much, John. Oh, a lot to think about there. If anybody's got a question, then it's probably best for me to field them, depending how many there are, of course. And if you use the reactions button and do a thumbs up or something, then it'll appear at the, you'll be promoted to the top of my my list, and then I can cue you in. I do have one question. Well, I've got 3 actually, but to start with, is there anything to be gained by all of the observers using a GPS timestamp? Then that could take some of the timing error out of the observations. Has that been considered? Or is that going to be helpful?
Hadn't been considered. I mean, we ask our contributors to use an online service at least, and many of us use the same. So for instance, actually, many of us use Dimension 4. Many of us use, I think it's Net Time. So we tend to use similar services. And I actually do believe that probably, although happy to be corrected, we're probably all within half a second of each other, which is a long time. Because if it's plus or minus half a second, you know, it's starting to spread a bit, isn't it? Time is important, and we do need to make sure we get the times right, especially when we're trying to look at video and radio. But I'd welcome thoughts on how to improve time.
Where does the, yeah, I do have a question. Oh, yeah, Peter's got one. Hang on a minute, Peter. John, where does the video data come from?
Well, currently I've only got one. So I noticed from last week's session, Fripon have data. So I've been using the, is it the net mode data? And what's the name of the chap who gave me access to the data? Come on, John. You'll know his name. You'll all know his name. His name is Michael O'Connell.
Yeah.
Yeah. Oh, there he is, look. And so,
Meteor.
yeah, and for that one match we found currently, because it was quite a recent event, I only got one line of data for it. But as more people submit their data, then UFO Orbit will take that data, and obviously the more lines it has per event, the better the data gets. But it's a reliable source. But Fripon apparently has the data. I haven't really looked there yet. I'm just starting on this endeavour.
Right. Do you want to unshare your screen?
Yes, certainly. Of course I will. I will stop sharing. There we go.
Okay. Peter, I see you had a question.
Yeah, I'm not okay. Are you getting me? Yeah.
Yes.
Yeah. At the radio telescope in Mannheim, I used to use a GPS disciplined 10 megahertz frequency standard. And it used to kick out, obviously, time data, which we used to log for radio meteor observations and other things. It is most certainly advisable to log GPS time stamping. And today you can get a USB cable with a GPS receiver on it. We're usually with a magnet underneath, and you can receive very easily GPS data. It gives you your exact position, and also you can take your timestamp. That's the first thing. With radio meteor data, what's also quite interesting is as the meteor comes through the different atmospheric layers in the ionosphere, you will find that strip ions are generated more or less. So it's a good idea to also monitor the RSSE, or signal strength, from your receiver, and to make a rough mapping of the signal strength as the event takes place. Because what you're actually looking at, you're looking at a sudden enhancement of signal, SIS, and this signal, there is a recombination time that the strip ions recombine with their atoms, and obviously this happens faster or slower, and you get some pretty interesting patterns from the recombination times that you see. So that's also something which is worth thinking about. With GPS time, very, very cheap. You can get through Amazon or whatever, you can get a simple GPS dongle with a cable and software that goes with it. So you can look at the stuff, get your exact position, and also you can use your time data. So that's my personal recommendation to you guys.
Thank you. Very useful, that.
Thank you very much, Peter. Andrew Letley.
Hello, can you hear me?
Yes, absolutely.
Loud and clear.
Excellent. Well, I wanted to squeeze in a couple of questions, actually. Well, first of all, I wanted to say thank you, John, for a very interesting talk. I absolutely found it fascinating.
Thank you.
Got a couple of questions. First of all, I'd be interested in knowing what database software you use to hold the data. And my second question is that where you've got a couple or more potential observations which you think are a match, what scope there is for deriving velocity data from that.
So the first question is easy. I'm using MySQL. It's free, well, it's virtually free, and it will hold a lot of data, and it's pretty damn quick. The second one, I don't know is the honest answer. I'm hoping people here can help determine what more we can do with the data that we have, or indeed, do we need to collect extra bits to make it more worthwhile? But I guess if you can match a video and a radio event, then potentially you can do even more information. But again, I don't know. That's honest, isn't it?
Yep. Thanks.
Yeah, thanks, Andrew. Mike German. Oh, you're mute.
Okay, right. Yeah, my question, or it's more a comment, relates to the fact that nowadays most people use SDRs in their radio and in their computer, and also run software. And in doing that, there's a built-in latency or time delay associated with any signal that goes in there. And so when it's recorded on the PC, this delay needs to be taken into account for accurate timing. It on my PC, it probably amounts to 250 milliseconds, but it could be more than that. And I've yet, and I'll be talking about this a bit later, that's all. And that's what I wanted to say.
Yeah, interesting. Yeah, thanks, Mike. Yeah, I'll come back to you shortly after we've run through these questions for John. And you might. Oh, Peter, you got another question, a supplementary.
Yeah. I used to have a network in Germany. I went to the regulatory office and got 3 frequencies allocated for radio Meteor work. I was using ex-German army transmitting equipment, which was for vehicles. And I had a frequency around 30 megahertz, another one around 50 megahertz, another one about 79 megahertz, which is basically the military VHF band. And what I had was, I had at a distant location, I had 3 transmitters that were running 24 hours a day. And at the receiving station, I had 3 receivers that were listening as well. So you get very different events. If you're looking at the event and you're recording the event, you will find very different events according to what frequency you use. The lower VHF band is, so to say, the one that will detect everything. The higher you go up in frequency, you know, you got really big events which are visible, and the little events aren't visible. In Europe, everyone is running to listen to Graves, which is the French radar transmitter. Great stuff, but I see it as not really the bee's knees of what we should actually be doing. So one important thing is to, if you're using forward scatter radar, which is what we're doing with a forward station that's transmitting, and your receiving station distance away, and you've got the volume between transmitter and receive, that's the area which you're actually monitoring. I used to do 75 megahertz, which was the marker beacons by airfields as you're coming in. Unfortunately, it turned the power level down dramatically. With a sensitive receiver, you could probably still observe big meteor events using the marker beacons for ILS approach, but it's no longer reasonable to use it. There was the 50 megahertz band 1 TV transmitters. I used to use one in Vilnius, which is up in Litauen, Estland-Litauen area. And that was very, very good indeed. So when you're doing your radio Meteor observation, you really seriously have to think about your radio path profile. Which area of the sky are you covering? Where's the transmitter that you're using for forward scatter radar? Yeah, and also what frequency you're using. Many of the really weak events, you can't observe them with, say, 140 megahertz or wherever Graves is sitting, 150 megahertz. You just get it only gets the larger reflections. So that's just what I want to say about that one. It's great doing computer software to do all the processing of data received, but you've actually got to concentrate on the hardware first to get good results. But both things go hand in hand. That's it.
Thank you very much, Peter. Paul Hyde. You're mute, Paul.
Right. I was pressing the space bar, which I thought unmuted, but it doesn't. Okay, apologies for that. So a couple of things, one of which Mike German alluded to on the timing issues. We don't really understand the performance of Spectrum Lab in that respect. We know there's a couple of enormous data buffers within Spectrum Lab, which are there because of Windows' habit of going off and doing housekeeping work. So to keep the stream going, there's as I say, a couple of large data buffers in there, and we don't know how data stamps are associated, or time stamps rather, are associated with the data. So that's a question mark. And then the other bigger thing is with the Graves or Graves radar. It's a fantastic searchlight scanning the sky, but it is scanning, and you will only get a reflection off a meteor trail if it's illuminated by the searchlight. And the fact that this searchlight is scanning across the sky means that observers can possibly see the same event at different times. And it's a 4.8 second cycle. So there's the potential for significant differences there. So that's my bit.
Yeah, interesting. Thanks, Paul. Albert White, I see you've got a question.
Yeah, thanks very much. I better turn my video on as everybody else has. Right, a couple of quick ones just regarding the timing in Spectrum Lab. I mean, there are radio time beacons around on the HF spectrum, certainly. That I wonder if just by noting the time the Spectrum Lab records against those times, which would be fixed, would be interesting to give that time delta. The other thing is really follow on from what Peter was talking about, using different frequencies. The amateur radio community seem to predominantly use the 6 meter band for them, which is about 50 megahertz. That's where most of the Meteor communication is happening. So I was wondering if you know, to aid this endeavor, that it would be worth talking to some amateur radio stations and perhaps Ofcom as well, to set up a beacon during a major, you know, the Perseid shower or something, and use that maybe for some almost calibration data, just seeing exactly what we're able to see from where, by having control of the transmitter as well as the receivers. Now, it's going to be a lot lower power than Graves, and I'm sure there's permissions, things to be worked out, but it might be something worth looking into. Thanks.
It sounds like a great idea.
Yeah, that's well worth exploring. You got yourself a job there, John.
I have, haven't I? Job for life, really, which is great.
We've got one more question from Peter. Make it short, Peter, because I want to move on.
Gotcha, right. Could it be, Paul Hyde, you made a radar, an active radar system with a transmitter and receiver? I think I can remember something in the book which came from the UK where someone actually made an active radar for radio meteor work. Was that you, Paul?
No, definitely not. I think it was, if it's what I'm thinking of, I think those ideas were purely aspirational and never ever made it into actual operation.
Aha. Right. 6 meter amateur radio, also 4 meter amateur radio, which is up at 70 megahertz. So you've got 50 megahertz and 70 megahertz, roughly. It is actually part of the amateur radio hobby is radio science. And some amateurs in the UK actually do ionospheric sounding to see what is the maximum usable frequency, lowest usable frequency of the ionosphere. So they are actually open to this kind of stuff. and it should be possible to get radio amateurs to use CW carrier wave transmitters. The only thing is it will obviously need a carrier wave CW identification. So the Morse identification of the transmitting station needs to be regularly transmitted. But this is actually part of the hobby. So it is something worth looking at. And they've got the two frequencies. I think 52 megahertz and around the 70 megahertz. So it's exactly what we need. If you go up to Graves by 2 meter frequencies, my experience, it's too high. You need frequencies below 100 megahertz. With FM radio, that was also an idea. But obviously, FM radio, the stations are all over the place and all the channels are full. So you can't find a free channel to monitor with. That's the big problem with FM radio. Okay.
Thank you, Peter. Michael.
Folks, thanks, John, for the talk. A question maybe for the group is in terms of, and Peter, it was something you had mentioned briefly before we started, was the issue of interferometry, and could that be used using multiple systems like we have, in a more perhaps coordinated way for purpose of determining the location of a meteor?
We have passive radar systems today. If you want to do covert observations of aircraft and flying objects, today I've been working on, in the past, passive radar systems. You are correct. You have a number of receivers and they are all on the same location. And through the phase delay that you have through the different antennas, you can actually find direction. If you go to systems like LOFAR and SKA, it's the same in green. You're listening to a signal and you're listening how it comes at different times into the dipoles, and you've got a time delay. And by putting into a super cray, you can look at the whole sky and you can receive everything in every direction. And then at the end of the day, hundreds of scientists can say, hey, I want to observe the Crab Nebula, or I want to observe Cygnus A, or whatever, and you pick it out of the data. So that is like passive radar, and it's used for radio astronomy. So if you're looking at meteorites, they are passive things coming into the atmosphere. So you need energy from somewhere. So you could be using radio transmitters on different frequencies and listening for the signals coming in. It works with passive radar, but I don't think it's possible with equipment that's available to amateurs today, because even though we've made great advantages in quad core computing with amazing clock frequencies, it's still not really up to what you can do. So yeah, future. But you're right, it's worth looking at.
Thanks, Peter. Andrew, you have another question? Andrew Lutley.
I think it's the other Andrew. I think it's me. One of my questions has been asked. The other one to John: do any of your contributors monitor using the Belgium?
Yes.
Rams.
You probably know him, Martin Rigby. So he actually uses both transmitters at the same time. He has two setups, one for Graves and one for Brams, and he does tend to get the same results. I've never tried it actually. Maybe I should, but I think it's quite low power, and I'll probably need to improve my antenna a little bit. But yeah, it's a possibility. And I did try to answer on the chat, but I didn't know how. I was trying to just answer your question, but it didn't seem to let me do that. So I apologise for that.
It says type message here.
Yeah, but that's at the bottom. You see, I thought, well, people, if I reply yes, who's going to know what I'm talking about?
Yeah, which
Anyway.
Yeah, I don't know how you reply to a previous.
No, I've got.
We'll work it
No,
out
I've
in
got no
due
idea.
course.
We'll
Still
get
early
better at
days.
this. Yes,
Still
absolutely.
early days for this group working with Zoom together. Although some of you probably live on Zoom during the week. Okay, we're going to move on, and Mike German has got some a presentation for us, and Philip Norton. Philip, are you with us? Is Philip with us?
Yes, I'm here. I'm
Okay.
here if you can hear me.
Yeah, loud and clear. I'll get Mike to present first, and then we'll come to you when he's finished and when we've finished with the questions that he generates.
Okay,
So,
can I can share my screen, good.
Yep, should be possible.
Right, what can you see?
Yep, endeavours in understanding the experiment.
Okay, okay, good. Right, well, good evening to everyone, and many faces are old faces that I knew, but there's that I know, but there's lots of new ones that I recognise from the last meeting. So I hope you're going to listen to me because there's lots of things here that match some of the things that have been talked about, and hang on, I need to. Right. So I live in the Peak District, and my main interest is in radio astronomy, basically radio meteors. But in the past, I have done some work on VLF propagation during eclipses. My overall objective is to understand what the signatures that we get from Meteor measurements using the Graves transmitter, what they actually mean. And so I'm going to be talking about my endeavours to understand the experiments. And I see this as the three elements to this. There's the transmitter, of course, the Graves transmitter, the meter itself, and the receiving station. And it's the first two that I'm basically going to be talking about today, but obviously it does pull in some measurements that I make. And this kind of matches in with an overall approach to this with other endeavours that I have, and I'll touch on those right at the end. Right, those of you who use Graves will be familiar with this kind of signature that we get on a spectrogram. It's definitely a meteor, but what caused this kind of signature? And so we need to understand the experiment. Now, this is the transmitter. First thing to note about the Graves transmitter is that it is a French military establishment, and very little is openly published about it. And you could suffer the pain of PV if you actually enter the site. But there's lots of amateur sleuthing work that's gone on. It's available on the internet, and hopefully it's of a factual nature. So here we see the back of that there are 4 panels associated with the Graves facility, which are basically beaming south. And the 4 panels cover 45-degree sectors here. So this is what I call sector A here, the one that points in this 45 degrees, and that's this panel here, or this one here. The Graves switches in 7.5-degree beams, and the beams are synchronized such that this sector here, which I call A0 and B0 and C0 and D0 all switch on at the same time. And then the A1s, and they switch on for 800 milliseconds. Then the next subsectors come on, A1, B1, etc., and then on to the next set until you've gone all through the 6 sectors, and then it goes back to the beginning. The interesting note that I've made from the internet is that there's a phase change when the beam switches from one sector to the next. Now, the beams also found that the beam sequence is accurately time synchronized. All of the 0 subsectors start with the first second of the hour and then go on from there. So, oh yes, I just wanted to point out that in this picture here, you will see that behind the antennas, there's lots of clutter, the transmitters, power supplies, and lighting, etc. Right. First part of this trace, incidentally, here is the head echo Doppler signal. And it's not part of the Graves artifact. But the 11 spikes after this are due to the phase change produced by graphs when the beams are switched from one sector to the next. FFTs, such as we use in spectrograms, Spectrum Lab, for example, sees these phase changes as discontinuities, and it generates these spikes. The 11 spikes coincide with these beam switches at intervals of exactly 800 milliseconds. So here I've overlaid those subsectors and sectors over the map with graphs in the center. So to the south, this is the intended operational area for graphs. The subsectors you can see marked on here, all the way around here. We would expect this design direction to have beam widths that are well defined. And the subsectors, as we've seen, relate to the not only to the bearing from graphs, but also that time sequence, and we'll come to that later. We also know from studies such as that of the ISS that John mentioned, that graphs radiates to the north. Hence we get ISS and meteor scatter, but we know little about those patterns. It's most likely that there are rear or side lobes associated with the rear antenna panels. We cannot assume that there's the same match between the actual sectors that I show here. These are the northern sectors, which I push over diametrically, yes. But we'll see that the sequence does follow round. And so the actual radiation is unlikely to be contained within these subsectors. But for this exercise, I actually I'm going to start again. To investigate these subsectors and time sequences that we've got here, we need a relationship between the positional data, the bearings here, and the timing data. And if we look at this signal broken out into a using here I use the Meteor logger software, and it produces here on the plot I'm showing Doppler frequency and signal frequency in green. So taking first the red, the Doppler shift frequency, we see the head echo coming down here. We see the and then we come to the specular reflection point and the main trail of the meteor. You might spot some little blips here, again associated with those discontinuities that the FET sees. On the green plot, the signal level, we see that as the head echo approaches this specular point, the signal level goes up to a maximum, and then we get the strong signal from the specular scatter. Also, we'll note that there are changes in amplitude here, 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 and so forth. These are on the bottom here. We've got a time scale, and this represents about 8.5 seconds. So quite a long signal. Okay. Right, now if we correct the logged times that Meteor Lab has produced and allow for the latency of the system, we can align the signal levels, these changes, with the sequence of beams that we get from, or pulses that we get from graphs. And as you can see, they align very nicely, and it is necessary to correct the times, as I say here, to allow for that latency in order to bring things into synchronization. Now, the adjustment I made for this was around about 250 milliseconds, but alignment would also have been achieved if I'd added 250 plus 800 or 250 plus 1600 milliseconds. The head echo occurs in one of these sectors, the 0th sector, but we can't tell which subsector that occurs in. The location of the data is required. The meteor location is required to link the time sequence and the subsector positions. It's also interesting to note that the signal levels within here aren't actually tracking the meteor across here. It's really the FFT taking a number of data points across there. So I had been using this example to calibrate in a bit more detail the ISS data that we were getting for the collaborative database. But then I found that there was a match with a video event on the IMO Fireball database. And I found this event overlapped the radio start time of the record I just showed you, and it lasted a similar time. And this is one video event from the nematode camera. Now, John Berman found another one of these nematode records, and he calculated the track for this. So you can see it's right within his area of interest. He calculated the speed of about 19 kilometers per second. And also there were 4 or 5 other possible matches on the radio Events Collaborative Database. Oh, and the first camera that caught this was based here, just near Brighton. Then, at the last, or the first RAG Zoom meeting, John Louis informed us that the Frippon database was now online and we'd actually use it. So I checked there and found it was caught by 3 cameras on the Frippon. This one here, this one here, and this one here. And what looks like a close match, the track passing through just above Graves and ending up below Ghent. The speed, as far as I could tell from those, was quite similar. And if we match the two, I think that's a pretty good match. If I go on from there, I drew this rough sketch of the track of that meteor, the combined track of that meteor, and matched it with the subsectors that we've been talking about, the subsectors to the north. So you've got B0, and I've shown the complementary one on the timing data here, and it looks quite promising to start off with. But unfortunately, it didn't work out that well because I was unable to reconcile all of the differences, times and speeds of the meteor, and I have to conclude that there is a general issue with the direction of the beams in this northern sector. On an aside though, if I can locate from the video data the position of the head echo, is going to help me with another one of my endeavours, which is to validate a head echo computer model that I wrote a couple of years ago. So in conclusion, this kind of proof of principles approach shows that we can align beam switching with meteor data and provide a route to improve time accuracy. So we can get that from the actual data and the times given by the graph's signature, if you like. I think that I knew that the translation of subsectors from the south to the north as a single formed beam was wrong, and the antennas undoubtedly have side lobes. There's also an ambiguity in the time correction that I made for the meteor event, and this will be resolved with a more practical, exact method of latency calibration. This is my first opportunity to compare video and radio events in this way, and it produced more questions and answers, I think, but it was an interesting exercise. So it's not possible here to reconcile radio and video positions. I need some more meteor events, and hopefully from south of Graves, to actually get a better handle on all of this. And if I'm able to tie the head echo data in, then I'll get another of my hit lists to work on. So my continuing endeavours to understand the experiment, different aspects of what I've been doing here. Firstly, to use meteor logger data of ISS positions and the timings to map the southern subsectors, and then go on to further investigate the northern section. So that provides data of precise positions and times that we can then go on and further our investigations. Now, the ISS position data gives bearings from the receiver antenna as well. and we can also compare signals using matched antenna systems. So it's what I've, a bit of a mouthful, using simultaneous differential signal levels of angularly separated radiation patterns to provide direction. And basically consider the azimuthal radiation pattern of a half-wave dipole, cosine pattern. Then consider cross dipoles and the difference in signal levels that you'll get in a particular direction. Okay. Now replace those cross dipoles with crossed Yagis pointing vertically to give you a bit more gain, and you got the idea. This is an idea, and I'm pleased to see that Phil Norton is here. This is an idea that originally came from talks with him, so it's really good to talk about our thoughts. As far as latency calibration is concerned, I note that Whittam is with us today, and I've talked to him about this. I've almost built a system based on the NSF time signal station in the UK to modulate a precision frequency oscillator at 143.05 megahertz. And this will, I will inject directly into my systems, and it will provide me with a measure of latency measurement, also frequency calibration and amplitude calibration. And as I mentioned, I want to obtain some experimental head echo positional data to help validate my numerical simulation model of head echoes. So that's about it. Thank you.
Thank you very much. Thanks very much, Mike. Do we have any questions for Mike before Phil joins us? I have just a comment. I think many radio astronomers come into radio astronomy with their first experiment being meteor detection, and there's may well be a number like myself who have tried this and think they're measuring meteor reflections, and maybe or maybe not, because it's, you know, if you're starting out, it's quite tricky, and I can see there being some mileage in getting the experts together, such as yourself and Paul, with those that are like me, that have very naive questions, who are at the beginning of this journey, to help get, you know, to check that the data we've got is actually real. Because what I would like to do in the medium term, long term, is to send John Berman some meteor data that I'm collecting. But yeah, thanks, Mike. You've given us all something incredible to think about there. And I hadn't even considered the characteristics of the Graves transmitter before this evening. So you've really opened my eyes, and I'm sure others as well. Great stuff. Thanks very much, Mike. That's good. Look forward very much to the next chapter in your story, because this is it's an ongoing project, isn't it?
Indeed, indeed.
I see Peter's got a question. Peter, I'm going to put you on hold, and maybe hold that thought for a bit, and we'll see what time there is after Phil has shared his thoughts. Phil, the floor is yours.
Hopefully.
Yeah,
Well,
that's working.
That's better. You should have a meteor scatter with a sort of fuzzy meteor radar slide on it.
Yes.
Right. Well, I'm one of the people who actually contributes to John's database. I'm regularly giving him information on something like 10 to 20,000 meteors a month, which is the sort of level that we're picking up. Most of them are grains of sand, and I think John just logs them and forgets about them. But as he says, there's quite a few of the decent sized stuff. This is not how the meteor radar system works. This transmitter here is actually pointing south, as Mike says. We're picking up what's coming out the back of it. So our transmitter source is actually the rear lobes of the 4 transmitters as they sweep. And looking at Mike's figures, I seem to roughly agree with what I've got. So we'll continue. Meteor scatter's basically done with FunCube dongles now. Software-defined radios, nice and easy to use. Originally developed for the FunCube satellite. They weren't expected to sell many, but they've sold tens of thousands of them. I've got 2 of them running. I've also tried using it. I've got an AirSpy one running for a hydrogen line as well, but that's an experiment. These are my two aerials. Now, this may look stupid to some of you, and it really is. This is my graves facing one. With the element horizontal, I have the beam width, 3 dB beam width of roughly 70 degrees, pointing in the southeasterly direction towards graves. The opposite way around, on the vertical way, the 3 dB beam width is actually nearer 100 degrees, because that's the way Yagis actually work. So I've tipped it up at 30 degrees because I can still get all the way to the horizon, but I get more coming up. This one is my vertical system. It points straight up. That's why it's called vertical. The elements actually point north-south. So I pretty much get nothing direct from graves. It gives me a beam that's about 110 degrees wide east-west and about 70 degrees north-south. So I'm roughly covering from the M4 to the M62, somewhere near the Welsh border to the equivalent distance from Lincoln into the middle of the North Sea. But you can see how simple the systems are. I have two home-built preamps on these systems, realistically, because I can then run vast long cables into the house and keep the FunCube dongles and the computers nice and warm. As you can see, you need some really expensive computers. These are 2 that I got for about 50 quid each. They're both running XP. I can't be bothered with Windows 7 on here. They don't update XP anymore, thankfully, so these things don't get updated. I have a little backup battery here in case the mains goes off. So that keeps the preamps going. And that is my radio station. 2 of those, 2 bias boxes going out to the cables. And that's basically it. Now, this are the sort of things I get. You've got the Doppler east that way. You've got time coming down here. And the one question that I would like to get to, we think that duration is probably proportional to mass. The bigger the object, the longer it lasts. But that material on this bottom left-hand one isn't the same material as on the bottom right-hand one. The patterns look completely different. So my question is what I'm trying to get to is this one more dense, like it was an iron meteorite? was that carbonaceous chondrite, which isn't quite as dense? And is that basically a ball of gas and ice and literally got hot and went bang? So I'm interested in what the visible spectrum people are getting as well. Now, this is the meteor activity for last year from June to September. One thing that it's nice to see in the latest BAA handbook is the June Aerids. We have daytime Aerids peaking June the 7th, Perseids June the 9th. Then we have Boötids sort of later on, at the 27th. We also have the Capricornid shower at the end of July. August, needless to say, we get the Perseid meteor shower, and September, pretty much nothing. What you'll see, and I'll come to it a bit later, is the Perseid peak is quite wide. This is meteors per hour on this scale. Now, looking overhead, basically the June Aerids and whatever else we've got there pretty much covers all the morning, most of the month. July, the Capricornids is still there overhead. The Perseids just get wider and wider and wider, and you still do get quite a few September meteors. Now, moving forward to Quadrantids 2021, the overhead on this picture is here. The radiant is there, and it's slowly moving towards the overhead position. The south-facing system, you can see how the number of meteors per hour is slowly building up. And just as we got with the optical system, where you don't look straight at the radiant because you don't see anything, as the radiant goes through the beam, through the overhead position, we get nothing. It continues to grow until about lunchtime, when we hit 113 meters per hour. By now, radiant is low in the northwest. And I know from some of our colleagues at the Lincoln, Nebraska Astronomical Society, it continued to get better in the afternoon. I've expanded the scale here, and you can see that when they say the Quadrantids is visible on one day, yes, it is visible on one day. Either side of it, there's pretty much nothing. Overhead, the zenith-facing system, we still get the same null, still growing, and then it disappears. Overhead, still nothing. And this is the sort of information I put into the Radio Meteor Observing Bulletin, which is a worldwide system. And that's visible on there, hour by hour. These images are actually on the Lincoln Astronomical Society website. Just click on the radio telescope and you'll get what I've uploaded every hour. Now, getting a bit ahead of Mike and John, back in December 2012, we had what I call the Mablethorpe Meteor. I am just there. That's Mablethorpe. So needless to say, it's called the Mablethorpe Meteor by me. These are the two nematode cameras. So they have put the meteor there. So in theory, me pointing southeast from my south system, I'm not really going to be pitching it up much there. My east-west system, which realistically is covering that sort of area, I should get quite a good signal. As I said, the south-facing system didn't get much. Well, it was pretty much straight overhead in the fireball, so what do you expect? It just blew the vertical system apart. But what I'm doing now to try and coordinate similar to what Mike's doing is down the length of this meteor, I use SpectrumApp Lab. We all trigger on a certain different level, and that trigger level the speed at which the meteor gets up to that level depends on the computer clock, the meteor, the distance to the meteor, and everything like that. But once it's triggered, I'm actually measuring the peak amplitude and frequency every Spectrum Lab cycle down there. And so I know that this signal, which is actually coming from the back of Graves, is going up and down with side lobes. I also know that it's not really white. That is not a filled-in system. It is actually on, off, on, off, on, off to various degrees, depending upon how I set the contrast and the brightness on Spectrum Lab. Because I'm doing this sort of analysis, I keep the radio, the audio file, so I can plumb it in again and sit and fiddle. So I'm trying to get from this to ideally what it's made of, using the spectroscopes they're putting on nematode cameras now. I have got one that hit just there at 5:45 one morning. So I know the radio pattern of that, and I know the actual chemical match of that, but I haven't really got many of them. I have a friend 8 miles south of me who's actually part of the visual meteor group, and between us we're thinking of trying to gather spectra of the meteors, because at the moment we do see quite a lot of coincidences and some showers north of Lincoln between what Graham's got in his camera pointing north and what I've got, and we know from his angle that it's north of the Humber. So we know radio-wise, I'm definitely picking up meteors north of the Humber. And that's about my lot, I'm afraid.
Thank you very much, Phil. Does anybody have a question for Phil, or in fact for Mike German?
We've either confused them, Mike, or they've given up.
Yeah, Michael, and then we'll go to Peter.
Yeah, just a comment, I suppose, and to the group, I'll throw it out there that, and I as well participate in using Spectrum Lab and the FunCube dongle and feeding the data to John. And it's in relation to the the time scale on our charts. When we have a significant meteor event, we're dealing with a pebble-sized object which passes through the atmosphere over the course of a couple, 2, 3, 5 seconds. But when we see these extended reflections or signals, how much can we learn from that in terms of the meteor object, or are they really more an atmospheric event where there's turbulence in the upper atmosphere caused by the ion trail, for example? And should we really be analyzing on a very different time scale so as to capture that, in particular, that first 1 to 2 seconds and analyzing that part of the meteor event?
Can I answer this?
Yeah, you go ahead, Mike. I know you've been looking at it.
Well, I think that there are some events, the really long ones, that are caused by persistent ionization that stays up there and takes a long time to disperse and gets shifted around by magnetic fields, etc., in the atmosphere. I think there are other events that, if you look at them in detail with something like Meteor Lab, you obviously see the head echo, and you can also in the signal strength level on something that's less than, say, that 800 milliseconds pulse that you get with from graphs. If it's within that, you can actually see the Fresnel diffraction patterns that build up. Now, this doesn't tell you much about the meteor. It just tells you the geometry between the transmitter, the meteor, and the receiver. Whether one can tell any more from the nature of the meteor, it's one of my endeavours. Okay.
Thanks, Mike.
Did that answer the question, Michael?
Yeah, I think so. I suppose it's I suppose where I'm coming at it, I suppose, is from my background with the Meteor camera network and tracing the orbit of, trying to trace the orbit of the object back out into the solar system, which obviously from an optical perspective, we can see the light, so to speak. We can point the camera and we can record it quite accurately. It's quite a short duration. Radio obviously is, well, in my opinion, well, for me, I find obviously a lot more challenging.
Yeah, a lot of people use the FunCube dongle. In fact, I don't. I've got 3 systems using other matching SDRs and 3 different antennas to do these measurements. And I use Meteor Lab, so I get a lot more information than you would get from the Spectrum Lab. I think Phil has the right idea in recording the wave and then being able to analyze that data later.
And a question for you, I suppose, without hogging the question time, apologies. Question maybe follow on then for you, Phil, is that have you ever retrospectively gone back to analyze the first couple of seconds of the meteor event, just in terms of the rapid Doppler shift, and see what can be learned, maybe perhaps in terms of the velocity of the meteor or direction, and if there's merit in this as a group doing that to analyze our data and for various receivers.
I've not actually got into that. I've sort of left that side of it to Mike, so I know Mike's been looking at that, the head echo. I've just tended to look at the overall thing.
Okay, thanks, Phil.
One thing I didn't say in that presentation was the fact that I have got the 2 aerials gives me parts of the country where I can't pick up and parts of the country where I can pick up. And if you combine that with things like Mike, who's out Manchester way, and I know he's sort of pointing southeast as well, if he fills some of the gaps, if he gets it and I don't, there's a chance it's in the bit, we can sort of put it to within about 100 miles.
Yeah.
Yep, thank you, Michael. Peter, sitting patiently waiting.
Yeah.
You have a question?
Right, guys. I have been doing radio meteor observations since the late 1980s. I was working together with Jürgen Rendel from the International Meteorite Organization. And it was obviously very, very interesting getting to be with these optical observers from the EMO at a very early stage. And so let me fill you in on some details. If you have a fisheye camera looking vertically up to the zenith, you can video the meteorite events that are visible from your location. So today you can get very cheap CCD cameras, which are used for surveillance, and you can unscrew the lens at the front, and you can purchase for a very low price a fisheye lens that you can screw in. I think the diameter is about 35 millimeters of the screw thread, and it's the standard mass-produced camera, and you can get different lenses for them. So you put the thing on the.
Could I point out that you can get the ZW Optics CCD camera, the 120mm, which is what Graham's using. It comes with a 150-degree fisheye lens on it. And that's what we're using 8 miles away from me.
Marvelous. I'm using the old-fashioned stuff. I'm not as modern as you are, but I had a cover which was basically a half-round piece of metal, and it was with the windscreen wiper because the thing's on the roof and you don't want to take it in every day. So using the windscreen wiper, you can push over the cover over your fisheye. So you've now got an optical observation of the whole sky. This is very good because you can correlate it to radio events. Right. To do a fun evening for the Perseids or anything really interesting for the general public, you go back to analog technology. You take an FM radio, you tune it to a frequency which is not, you can't receive it really well at your location. What you do is you're looking at the sky and you've got the radio cranked up, but it's not producing any sound whatsoever. Suddenly the radio bursts into action, and at the same time you see the meteorites going through the sky. So that's very interesting. Go back to analog first before you go with SDR dongles and start getting deep into the software. Right. If you look at the old film about Jodrell Bank, the inquisitive giant, it's all black and white film, it will show you the building of Jodrell Bank. And it shows you a lovely, lovely piece where you see meteorites coming in and they're actually using active radar to observe them. What you've got to understand, the meteorite coming in is not the size of a marble, it's the size of a grain of sand. And it's coming in about 120 kilometers a second. So when it makes a light effect in the sky, it's around about a half a second, if you're lucky, that the event is visible. So it's a very, very quick event. However, the radio event is a lot longer. It's like 2 seconds or a half a second or 10 seconds or even longer, depending on what the material is that's come down. In general, if you've got an iron meteorite, it's going to come in as a brick. It's going to vaporize a bit, but if you're lucky, the brick's going to land on the ground. If you've got a stone meteorite or a soft material, it's going to break up. And at these speeds, you've got a lot of ionization of the atmosphere. So that would explain a bit of what you're observing. You're actually on the right road with your observations. Hang on, let's have a bit further. You've obviously got, with radio meteor observation, the optical guys, they only know the night meteorites. So when we are observing, we have totally new streams of meteorites, which the optical people just do not know because they take place during the day. If you go to the European Radio Astronomy Club website, erac.net, you will find a lovely calendar that we did in the 2000s, which gives all the daytime and nighttime streams. Okay, right. I have to come back to using Brahms or Graves as a transmitter source. It's nice for amateurs to be able to receive something, but due to the pulsed array, it's not really all that good for real meteorite observation. So Graves is nice to play with, you get some nice results, but I've got another idea that may be more interesting. If you were listening with a dongle, you've got basically a wideband receiver. So if you're listening to nothing and a meteorite suddenly comes, you have many transmitters which are around you on different frequency over your radio horizon. So you will suddenly see peaks appearing on all different frequencies. So it's maybe an idea to rethink, to look at your frequency spectrum, to identify signals that are there all the time, and then to say, okay, when they suddenly appear, and it's more than 2 or more than 3, then this is a radiometeor event. So that may be a better solution than what you're using with these wonderful transmitters in the south of France. Any more on my paper for notes? So the quick butchers, yeah, wideband monitoring. Size, fisheye lens, roof. Meteor. Yeah, meteor spectra. The optical guys are actually analyzing spectral light coming from meteorites as they lighten up the sky. This is amazing stuff. Back in the 80s, we only had video recorders, and this was just it was a very, very sporty thing to think about doing. So I think that's really, really interesting. So there are my comments on that. Yeah, back to you guys.
Okay, thank you very much, Peter. Is there anybody else that would like to share anything in this session? We've got a few minutes. And it seems maybe not. Okay. Next time we gather, we will be looking at solar SIDS and TIDS with Mark Edwards. If there are other of you that are doing SID observations and have got some data to share in the second half, in the poster session, that would be great and quite complementary to Mark's presentation. Just drop me a line and let me know so that there's I can cue you in and have some idea as to how much time we're going to need. Otherwise, thank you so much for your contributions. Just remember, if you want to keep the chat, now's the time to do it, because once the meeting's finished, it all disappears. So we can save the chat, and I will stop the recording, and that will appear on our YouTube channel in due course. Just before we finish, is there anybody that would like to say anything, to share anything? Otherwise, keep all the great ideas coming, and we can make this group even more useful than it is now. I've enjoyed this evening tremendously. More ideas than I think I'm going to have time to explore, but certainly motivated me to continue with my meteor observations and help me understand a little bit of what I'm looking at. Okay, I'm going to close the meeting and look forward to seeing you all next time. Please use the group, the radgroup.io to post comments and ideas. And if anybody wants to contact me offline, then my inbox has always got some space in it, and we can see where we go from here. thank you, all of you who have given me so many good ideas and encouragement over the last fortnight. We seem to have made a tremendous amount of progress. So stay safe and we'll see you next time. Bye, guys.
Bye-bye. Thank you.
Bye, thanks.
Bye.
Bye, guys. It was nice. I'm going to bed now. It's very, very late in Thailand.
Sleep well. Cheerio.